We had a brief encounter with subtypes during the lab a couple of weeks ago. You may or may not have caught that I tried to introduce you to the concept of subtypes in setting up our topology rules, but it turned out it wasn't necessary for that lab, so I went back on that idea later and told you not to bother with it because we didn't need to get into that for topology at that time. But I do want to talk about how subtypes are used in ArcGIS because it's a really great tool for managing large data sets, especially like a city infrastructure database. You can put a lot of controls in place in your geodatabase that actually allows you to manage your physical inventory or infrastructure. So essentially what a subtype is a specific category of your feature. So you've defined your feature classification system in a way that makes sense for a spatial management system. So say we're talking about a parcel database. There's kind of two ways that you could approach that. You could have a single parcel database. So a single parcel feature class. Let's stay in the geodatabase realm that allows you to put every parcel in your jurisdiction within it. And those are going to have a consistent set of fields throughout them. But if you looked at that on kind of a management level, it could be useful to you to manage your commercial parcels independently of your residential parcels, and likewise for industrial. So you could conceivably build 3 different feature classes for that. However, if they all have identical features, you're now maintaining 3 different structures that need to stay identical. And there's a lot of problems that go with that, right? So say I add a field to one of my data sets and I forget to add it to my other 2. Now, if I wanted to combine those back together at some point, I have this data structure problem of this doesn't exist in these other databases. So do I just add a default value to those? This is a data management problem. And it also becomes a little bit more difficult to run group computations on things. So if you want to figure out information that involves all 3 of those categories, you now have to join them back together. So a somewhat more efficient way to manage that would be to build a subtype. So now you're back to your single table of data, but you've created subtypes within those categories, and you can set up different rules for those subtypes. So when we talked about the emergent versus floating, some of you created 2 different shapefiles. So that's your situation where you've split your management of your features into 2 different groups, and you can no longer treat them as a single group. The recommended approach for the lab was to enter this information into an attribute field. So you can then take that a step further and classify those as subtypes for that field and apply some different rules and management to it. So one of the things that can be different for those fields is emergent fields could have different topology rules than floating. So remember the rule that we had that your emergent and floating vegetation couldn't overlap your uplands? Well, technically emergent vegetation is an emergent wetland vegetation type that can occur in both of those areas. So you could have a rule that said your floating subtype cannot overlap with uplands and keep the emergent out of it, which I think would have been a really great way to run that lab had you been introduced to the concept of subtypes. So maybe I'll think about reordering things a little bit next year. Anyway, you can also apply different domains to them. We're going to talk about domains in a second, but they essentially control the list of default values that can go, and the rules about your data input. And then overall, it increases the performance of your database because you're not creating more feature classes than you necessarily need. You're just further limiting the available options within a feature class that's essentially all the same. Does anybody have any questions about that concept? Because that's kind of a fundamental underlying database concept.
I guess I don't have a question necessarily just about, I mean, I get why using being able to combine them would be easier, but I attempted setting up the subtypes when I was doing that lab, and I tried it a couple times and I just kept getting like null errors, and it wasn't like making the two separate types, and I just ended up saying, you know, like, what the heck, it's not working, I'm gonna do two separate shape files instead. And it ended up being easier for me that way. So I mean, like, it seems like it's easier to just maybe I was going about it in a difficult way, but for me it was just a whole lot easier and less of a headache to not try to combine them and set up rules for them like that rather than just leaving them separate.
And I had
that was
that same
kind of the
challenge.
same boat.
Yep, same here.
So I haven't gotten to look at all of the topology rules yet. I would guess that in a fairly straightforward system like we were looking at, there's probably enough flexibility in topology rules that you could get away with it. But I'm not sure that you could extend that same concept in a more complex situation. So from a conceptual approach, like I said, you do have two different options. But from a data management approach, understanding the tools behind the database and the way that it's constructed gives you a lot more power and flexibility in implementing things in the long term. So kind of like I said at the beginning, yes, if I were going to create a really small data set with, you know, not more than 50 different vegetation areas, I would potentially not bother with a lot of this. All right, so this is an example of what a set of subtypes might look like. So this is a ArcGIS Pro kind of sample data set that talks about different building structures, I believe. Yeah, so we have building subtypes. So they've classified the buildings within this facility as either having development purposes, utility, marketing, security. So you can imagine, you can see right here, one of the things that they want to manage differently for each of those buildings is what's the public access look like. So for development, and obviously I can't move this right now, but for development, you want to have employee access only. You don't want to allow the public access to it. But for marketing buildings, you want to allow public access. For security, you don't want to allow all of your employees. You just want to allow your security, your employees that are classified as security. So this is one of the ways that we can use these subtypes. And then you can start to relate that to other data tables. Say you have a list of employees somewhere, and on a kind of an overall data utilization, maybe you have a map that shows different employee types, what they have access to. Just kind of speculating on how you might use this on a kind of a public facing level. But it also can help you manage how you approach all that infrastructure. So this is just one example of the hundreds of different ways that you could apply subtypes to a spatial data set. So one of the specific advantages of, well, let's step back a step. So domains tell your database what type of information can go in to that feature. So you've already defined your attribute field type, but now you're going to tell your database go one step further and tell it what can go in each of those fields. So this is where we start limiting to a list of choices. So on that one, you would set up a domain, which would be this access type table. And these are the only entries that can go in that field because you've defined a domain that goes with it. And then you can limit those by subtype and bring the two concepts together. So essentially, a domain is a list of ideas. So here we can look at the condition domain. So you could have a condition domain that said your asset was in good condition, use condition, needs improvement condition. And you can use that domain applied to specific subtypes, or you can use it across subtypes. So say we had a domain for, oops, the development, let's say development, where's a field in there we can use? Say we had an asset manager that only, a group of asset managers that only manage development type buildings. You could have a domain that was specific to the development subtype that was a list of those managers and would help you populate those fields. But then you had a different set of managers that managed your security buildings. You could then attach a different domain to your security subtype. Or say you just have a single set of facilities managers that you want to use across all of those subtypes, then you would attach that subtype to your maintained by field. It's kind of an awkward example because who has that many buildings and building managers, but it kind of just shows the relationship between your field versus your field subtypes and versus your data entry domains. So domains and subtypes can each kind of individually interact with fields, or they can all influence each other. And you can also utilize domains across different fields. So if you had a field that said red, blue, or green, and you had different applications for that set of classifications across your database, you could reuse that domain multiple times. And really what this all comes down to is managing large data sets and managing the quality of the data that you receive. It's kind of mind-boggling how quickly people can destroy a good database. I've been developing one for our geotechnical department on processing sediment samples. So let me think of a couple of examples. It's basically the end goal is to output this information into something that helps us draw pretty stratigraphic records for each of these sediment boreholes that we put out. So in order to get that automatically into the imaging software, I want to have consistent output of my information. So by forcing them to select from a list of colors, for example, I won't have somebody saying that they picked up blue sand, or I won't have one person calling the sand tan and the other person calling the sand mocha. those are kind of silly examples, but what it boils down to is if I limit the information that they can put in, I don't have to go back and fix it when it's a deliverable. And that's a huge time-saving thing for something that we do over and over and over. And in my mind, it helps illustrate how differently we all think also, because it really amazes me sometimes. The problems I didn't know I was going to have to correct. So we have all this complexity behind a geodatabase. And when you're thinking about this little emergent versus floating data set that you guys looked at, the question is very valid. Why go to such lengths for a fairly simple data set? And the answer is probably you don't need to. But you're then limiting the development of that data set that you've started for the future, right? So take, for example, I'm kind of in the process of developing a wetlands vegetation data set for myself. And I have sources of information on the vegetation types grouped by county in Alaska. You guys are familiar with county databases now. There's no spatial information tied to those. So the goal is to eventually tie it into a spatial information set. But then I have all these different shapefiles from years of doing wetland vegetation surveys that have nothing in common, right? There's no consistent means that I could use to relate those to these vegetation files. So at some point, I'm going to have to take all of these different shapefiles and try to make them consistent so that I can use them in a single reference for myself. All of this with the goal of streamlining future projects, right? So there's a threshold at which I've been doing this now for about 5 years. It hasn't been important enough to spend the time to build the back end until more recently when I had to do it more frequently. And what I want to be able to do is say, here's this region, here's the wetland types I expect to see, make me a list of plants I can take in the field. And oh, by the way, can you attach a picture to each of those so I don't have to remember what I was talking about when I'm standing in the rain trying to identify that grass. So that's a question of at what point does the complexity become valuable to you? It's usually more value to me at the end of 3 days of standing in the rain than it is to me when I'm looking at 3 months of winter where I can't go out and do these surveys. So it is somewhat of a question of prioritization. So again, when you have this simple flat system, it's not scalable and it can't help you address problems with bad data. So that's why we do database management. So this is kind of a conceptual look at relational databases. So we talked about the feature ID for ArcGIS data sets and having a key record in every table is important to understanding how those pieces of information relate to each other. So here we have a really interesting set of connections between the sports equipment that you choose to purchase, who purchased that sports equipment, and who shows up in the ER as a result of that sports equipment. So that's an interesting conceptual use of a geodatabase. And there's some database design problems I can see in this database. For example, what if John Smith breaks his arm the next week? Then I'm going to have another record of John Smith and his address in here. And what if his address has changed in the meantime? I'm then going to have John Smith with 2 different addresses but the same key related to these two different incidents. And that could cause some problems in sending my bill to John Smith. So part of understanding the relational database is understanding how you might use that data in the future if it's to expand, kind of foreseeing problems with bad database design. And there's some kind of underlying principles of relational databases that try to help you prevent some of those problems. But one of the keys is having a unique identifier, because I could at least look at the keys and see, okay, there's multiple entries for John Smith and the locations are different, but they're both number 42, so something must have changed. Maybe how does this look in a GIS database? Right, so we haven't had a lot of additional data sets outside of our shapefiles and our feature classes. But one of the things that you can put into a geodatabase or add to your project that has shapefiles in it is just a non-spatial table. So you can import a comma separated values file. I can't remember if you can add, I think you can now add spreadsheets. You didn't used to be able to add a spreadsheet, but we'll see if I can add a table of all of the Army Corps of Engineers permit actions. There it is. So each of these sheets in this table could be added to my spatial database. Because if it's a record of Army Corps permit actions, I would bet that there's probably a table in here somewhere that specifies where those actions happened. So I could relate that to a spatial database in some way, depending on how they code it in here. And then I could use that to relate all of this information to my spatial database. So I could look at the number of Army Corps permitting actions per county, information like that. So there we go. I lucked onto a good example on the first try. So when we put these non-spatial tables in, there needs to be a consistent way of relating them to the spatial database. But then there's two different ways that we can relate that information back to those spatial records. One of the more commonly used in ArcGIS is the join, because that appends the information to your feature table. But it means that you have to have what's called a one-to-one relationship. Otherwise, you end up with data loss. In this example, we have a list of countries, right? And we are appending the capitals to the initial table. So we start out with what's clearly an ArcGIS attribute table because it has a feature ID and the shape classification. And we want to add the capital for each of these countries that's in our table. When we do the join, they become permanently connected. But you'll notice, oh, they both have 7 records. It just looks smaller. If there was a country and capital relationship in this table that didn't exist in this table, it would disappear from the join table. So that's not necessarily a problem with your data set, right? That might be something that you don't really care about, but there could be potential for data loss. So this is what we call a one-to-one relationship. We have the same number of entries in both of our tables, and we end up with a relationship. So it's fairly straightforward to see Florida orange juice is population rank number 7. There's not a lot of question about how that relationship is going to happen. But you can start to have questions when you're dealing with more complex data sets. So here we have what's called a one-to-many. Again, this is fairly straightforward, right? For Maryland and the state oriole being the state bird isn't really a problem when we start assigning those state birds to different counties. You just end up with the same state bird in 2 different counties. Is that really the state bird of Maine? I feel like they stole it from us. But then when you have a more complex relationship, then it can start to get a little bit confusing, right? Going the other direction. If I want to end up with a list of only unique state birds, so now I'm going the other direction, you have to make decisions on which counties you're going to include in that list. So I don't know that I see this as the most obvious example of this problem, but you could start to see how, thanks, chickadee for Maine, not the mosquito. In other situations, if you were having to make decisions about which information you were going to keep, sometimes that decision is not the most straightforward. You know, we've chosen to use the county Howard. Well, what about Carroll? They've gotten thrown out now. So then you end up with what's a common database error, which is data loss. So you're presenting information as an output that's missing some of the information that you had to draw from. And that comes down to your database design, right? We should have switched the direction of our relationship to go this direction, because it's perfectly valid that you have multiple counties. So there's another option. Instead of a join, which appends that information to the table, is a relate. So you don't end up with this information permanently housed in the destination table, but you can still use this information in your interpretation. So you're still going to set up a link. So instead of a join, it's going to be a relate. And now you have this ongoing relationship that you can update the information in this table, and it will be related to your spatial table. So depending on what you're trying to achieve, it seems like joins are a little more common because they're kind of simple and straightforward, but they have a potential to create a little bit more data loss, depending on how you set them up. So here's what we can do with a database management system, right? We've kind of talked about the benefits and the trade-offs. Organizing and manipulating data is simple and straightforward with a small shapefile with a couple of features, limited attributes. But you can see as you start to mount more and more data into the system, it becomes a lot harder to individually manage every record, do quality control on every attribute that goes into every record. So by creating this database structure, you can start to control that, organize it, interpret it in ways that are helpful. So one of the kind of most simple, straightforward actions that we take on a database is sorting and selecting records. There's tools. Oops. I guess we'll get into querying. Tools that you can use for selecting based on attribute. This is a useful thing to sneak peek at if you're going to start to do some sort of gradient interpretation of your range of attributes, like we did when we were looking at the statistics of a data attribute tied to a spatial feature. So understanding the different data types that you can have within an attribute table, right? One of the neat things that we can do with this data, if we've entered it correctly, is to create calculated fields. So say you had a county where you had, well, okay, so this week's example, you have a county with crime rates, or sorry, a number of crime incidents within your counties, and then you also have your population. So we talked about what can happen if you represent your statistics and your populations are significantly different between these regions. Understanding how to create a calculation on the fly, you don't want to maintain this population statistic. You just want to be able to enter the information of how many crimes are committed and how many people live there and let it do the calculation. So calculated fields are one example of how setting up your database structure is really useful. But it's only as useful as the data that you put in. So for example, I started to look at some of this information for our map. So we have this select by attribute tool, right? It's pretty straightforward and easy to draw a box around Alaska and select all of Alaska. Except there's a trick to this map where I might not realize that my spatial projection is putting part of Alaska. Oh, no, that's not Alaska, that's Guam. All right, say we were in a spatial projection where half of the Aleutians were on the other side of the world. It's no longer quite as easy to select using our selection tools, but it could be really easy to select by attribute, right? So for this table, I can see using my selection, and I'm filtering by selection. That makes it a little bit easier for these to pop up to the top where I can see them. So by selecting this polygon, I can see state of Alaska is classified as state number 2. But say I want to select a state here in the middle of everything, that's not quite as easy to see. If I select by attribute, I can tell it I want to collect by state code everywhere that it's 2. And I've now, by using my attribute table, selected all of Alaska. But then I started to play with this and I thought, okay, what if I want to select by some sort of spatial attribute? So I want to select everything that's below 60 degrees latitude. So what I wanted to do was go to my latitude and go less than 60. But I got to this field and I've got all these weird begins with, ends with, contains the text. So what's the problem with this field for what I'm trying to do?
It's related to string values.
Exactly, it's text or string. So if you look at the field again, you can see there's a plus sign and a negative sign. The negative sign you might see in a number field, but the plus sign is not a number, that's assumed if there's no symbol. So somebody has set this field up as a text field for whatever reason. So I'm gonna have to be a little bit more creative. And I wanna say, okay, so I'm only gonna see things between probably 50 something and 60 something. So if I wanna see below 60, I can say begins with plus, because they're using a plus sign, +5. And now I've selected any county that started below 60 degrees latitude. So this is just a real quick example of how you can use your attribute table to select information. if I knew what any of these other features meant, I could select on class FP, which is equal to H1 as well. So I don't know what we've just eliminated there, but we've eliminated them. So you can see with a large data set, I've quickly removed a lot of information that's not relevant to what my search was. So you're going to be doing processes that relate around that, and you did a little bit in your last lab as well. But this is focusing a little bit more on what you can do with those attribute tables, how you can start to calculate fields based on numerical information. So I couldn't do any calculations on that last one because they were text fields, but if they weren't, you could start to do calculations as well. And then you can also use the field calculator for rasters. So if you have a raster data set with values assigned that you want to perform some sort of mathematical function on, you can do that as well. So now we get into querying. Well, we just queried by attribute. We kind of skipped over calculating, but the query functions that I just showed you are how you look up things from large data sets. So it uses Boolean search operators, which you're probably, hopefully already familiar with from your library science classes that I think everybody has to go through at some point. How to search a library database, right? It's another form of data structure. So you use Boolean search terms combined with a little bit more mathematical or spatial functions to select from each of your attributes and do searches. So if you're familiar with SQL language, you can use SQL search functions, or you can use this graphical interface to build your structures, your searches. So when I talk about Boolean search operators, you guys familiar with that? Do you remember that from when we went from card catalogs to digital catalogs for libraries? Just one example of how those are used heavily. So if you want to match up two different search terms, if I want to find all of the counties that are in Alaska and below 60, I used essentially an AND tool, though you don't necessarily see it in quite the same way in here. So I told it I wanted to find a state 02, and I wanted to be, let's be above 60 this time. Right, there's no and or function on here, but I can switch on my SQL and you can see I have an and here. If I want to change that to or, I can now search for either or. So if there's anybody above 60 outside of Alaska, they would become highlighted, but they weren't, not even Maine. So let's try another one. Sorry, I should have applied that and saved it instead of, oh, well, of course it didn't find it because I said state FP. Let's use my class FP, whatever that is. Class FP is H1. Well, let's just see what happens when I use that. That's a lot of the country. If I add the latitude, I lost everybody, but what if I go just through the 50s? All right, Looks like there's a lot of H1s up here, whatever those are. But I've said and, so now we've lost Alaska. If I said or instead, now it means either one of those functions, and I can add that data set back in. So those are Boolean search terms. That's SQL code. So you need to enable your SQL search. And this interface looks a little bit different than the one we used to get. So that's why I wanted to highlight that for you. So those are the functions of an and or search, or obviously a not search. So if you were looking for opposites, you can use a not term in your search. So can you guys figure out what you would enter if you wanted to limit to residential in the base zoning field? What would that search function look like? We don't have to have exact terminology, but in general.
Well, it looks like there's a residential button in that little selection right there.
Yeah, so this window shows you the list of entries in that attribute field. So it'll automatically populate from your table. Unless it's a really big table, then it will ask you if you want to populate all of them, because it takes some time. So when we're scripting our search function, we need to identify what we're searching. So what would we search? Maybe if I put it in a little bit more familiar terms. If I want to search for Alaska, what would I enter in my search field? I would search from TL 2019 US County where?
State, or just A for Alaska?
So state is correct. I'm going to search my state field because that's where I've identified where each of these counties occurs in a state. So I would say select from TL 2019 US County where state, and then what would I do?
Equal with O2?
Yeah, equal to. So this is a numeric function or a numeric list. So we can use the equal functions. If it were text, I would want to use like instead. Does anybody remember what I put in for Alaska? I cheated, I looked at it ahead of time.
02.
02, there you go. So select from TL 2019 US County where state equals 2. So that's a pretty basic SQL function. You can combine that now with and say and class FP equals H1, or sorry, class FP is like H1. And then you can add in, remember the wildcards that we looked at previously? There was the percent, which lets you search any length of fields. So it starts out, I said like, so it starts with 100, and then it can have whatever behind it. So anything that matches that would show up. If I said like 1004 followed by the percent symbol, then I would get this list here of Columbia to Texas Street. If I only want it to be wild on one character, I would use the underscore symbol. So I think you're going to be doing that, a little bit of that in your lab on Thursday. And some of that you can do using the other entry method in ArcGIS Pro, but you saw you got limited then fairly quickly in your select by attributes. It doesn't have an and or function, for example. So you can't, oh, I'm sorry, I lied. It's right here. You can't use some of the more complex SQL code functions. So right now, it's a pretty straightforward SQL statement. If you wanted to get into something a little more complicated for your selection, you can go in and directly code it. So I can't remember which method the lab tells you to use for selection. It would just be aware that you can use both. Okay. That is it for spatial databases. Next week, or sorry, that's it for database structures. Next week, we'll talk about how we use the spatial functions. Does anybody have questions on any of this? Have I sold the idea that it does begin to matter how you structure your data when you're looking at very large data sets?
Yes, I think so.
For example, you know, we ran pretty quickly into the problem of we're limited on our search functions for what's essentially a numerical feature because it was entered as text. So I can't perform greater than or less than. I could probably put together some really complex string that said look for +4 and +5 and +6 and use some wildcard in there and still get at it as a text field, but it complicates things. So it would have been nice to define that well. Another thing you're going to run into is, you know, a lot of misspelling or misentry of fields. So like fields like these are things that I would want to set up a domain on, you know, a domain that says only H1 through whatever. I think this ends in like H4. So it doesn't allow you to enter H11 accidentally, because those would then never show up in an H1 search. So.
Possible to reformat a text string into a integer string or a float string if you know that these all are numbers?
I don't think you can reformat, but you can, I think there's some geoprocessing tools for that. I'd have to, it's been a while since I did it in ArcGIS. I'll do some experimenting though and let you know how you would do that. It would be something like text to numeric. I'm not sure. I have to play with it a little bit. Because you'd also at the same time need to deal with that plus sign. Because ArcGIS wouldn't know what to do with a plus sign in a number field. So, all right. I'll be here for a little bit if anybody has questions. Otherwise, we're good.
Thank you.
Thank you.